So I'm going to try to do 3 example problems in this video, dealing with buckets as well as pulleys. These will be the last 3 examples I do, and then I'll set you off on your problem set. All right, so question 1. A 5 kilogram bucket is pulled up by a rope, accelerating it at 2.6 meters per second squared up. Determine the tension in the rope. So this is actually just like elevator problems. Okay, almost exactly the same, except instead of a normal force pushing up a person on an elevator, it's tension force pulling up a bucket. It's a heavy bucket. It's probably something heavy inside of it. So I'm going to start with the free body diagram. So there's the bucket. It's got a force of gravity down, and it's got a tension up, and I know for sure that the tension is larger than the force of gravity because of the acceleration. Okay, always important whenever you're solving these problems to know is it accelerating or not. If it is accelerating, which way is it accelerating? It says it's accelerating up. Therefore, in the free body diagram, the upwards forces must win. Okay, I can write out some values that I know. Make a list. So I've got the mass of 5 kilograms, and I've got the acceleration, 2.6 meters per second squared up. I have to find the tension, so I'll list that as a question mark. And to do this, I will apply Newton's second law. Net force equals ma. The net force only, there's only 2 forces on the free body diagram, so the net force is just what happens when you put those 2 together. And since tension is bigger than gravity, I'm going to write it as follows. The net force is the magnitude of the tension minus the magnitude of the force of gravity. Okay, and that will equal to the right side of the equation, which is mass times the magnitude of the acceleration. Again, I'm doing things in terms of magnitudes. The force of gravity is mg. Okay, that's our formula for the force of gravity. So if I isolate for tension, all I have to do is add mg to both sides. And I can fill in the values. Before that, I'm just going to show you one more math thing. There's 2 terms here, and they both have m in it. So something you can do is common factor. It's not terribly important to do that. It's a skill, though, that you want to always remember factoring. Okay, I'll fill in the values now. 5 kilograms for the mass. Acceleration is 2.6. G, gravitational field strength, is 9.8. And then I calculate that out with a calculator. Just bear with me for a bit. Five times bracket 2.6 plus 9.8. Okay, I get 62. So that's the tension, 62 newtons. And then we just complicate things in the next problem by having 2 buckets tied together. These are vertical buckets. So I've got the top rope is holding on to bucket A, but the bottom of bucket A is has another rope tied to it that's holding up bucket B. Okay, so 2 buckets, 2 ropes. And the question says, if the upper rope pulls at 120 newtons, so this top rope here is it's got a tension of 120 newtons. A, determine the acceleration of the buckets. B, determine the tension in the rope joining them. So starting with A, the quickest way to do this, in my experience, is to just simplify the question and think that we have 120 newtons pulling up both buckets together. Okay, I'm going to combine the 2 masses of the bucket together to treat it as one big object and just calculate the acceleration of that one big object. So I'm going to draw a free body diagram where my box represents the total mass of these 2 buckets, 8 kilograms. Okay, and that's got the force of tension up at 120 newtons, and it's got a force of gravity down, which I'm assuming is going to be less than the force of tension, because it says the buckets are going to get pulled up. All right, so that's enough to get the acceleration. I can apply Newton's second law. Acceleration equals net force divided by the mass. The net force, in this case, it's going to be the tension, the magnitude of the tension, take away the magnitude of the gravity. Okay, that'll be the net force divided by the total mass. The force of gravity, I'm going to replace with mg. And then I will fill in the values. This is going to get kind of messy here. So 120 is the tension. Take away 8 kilograms, the total mass, times 9.8. All divided by 8 kilograms, the total mass. I will type that in the calculator. Giving me 5.2 meters per second squared up. All right, so that's part A. I'm just going to try to block off a section where I can do part B. So the buckets are accelerating up at 5.2 meters per second squared. Part B asked me to determine the tension of this middle rope here. And to do that, in my experience, the simplest way to do that is to now draw a free body diagram focusing on one of the buckets that the rope is attached to. It's your choice which one, but I believe that the bottom bucket will be simpler. So 3 kilograms is the bottom bucket. So if I focus just on the bottom bucket, well, it's got its own force of gravity. And the bottom bucket is attached to a rope at the top. And I'm trying to find the tension of that rope. Knowing that my acceleration is 5.2, because we got that in part A. All right, so I've got to find the tension. That's my goal. I can do that with Newton's second law again. So since I'm finding out a force, I'm going to use the F net equals ma version of Newton's second law. Keep in mind that we're using 3 kilograms for the mass this time. The net force is going to be the tension take away gravity in magnitude. Equals ma. And then isolate for the tension. Actually, this is just looking exactly like problem 1. And then just replace the force of gravity with its formula, mg. I will common factor out the m again, so you don't have to. And now I'll fill in the values. So this is 3 kilograms, and then the acceleration 5.2 plus 9.8, giving us 45 newtons. Okay, so the middle rope only has a tension of 45 newtons. It's not nearly as tight as the top rope, because the top rope has to bear all of the weight, whereas the bottom rope only really has to bear the 3 kilogram mass. All right, so those are 2 bucket examples. These were buckets going up. Okay, I can ask you to do problems with buckets going down. These are accelerating buckets. I can ask you to do buckets at constant velocity. I could tie 3 buckets together instead of 2 buckets. So those are the different variations we can do there. All right. Last question is a pulley question. So we have a table here, and on top of the table there is a 6 kilogram block. It's tied with a string to a 4 kilogram block, with the string going over a pulley. Okay, and the 4 kilogram block hanging vertically down. So when I let go of this, so this is starting at rest, and when the person lets go of this, the 4 kilogram block is basically going to fall down and pull the 6 kilogram block with it. The 6 kilogram block will slide across the table. They're going to move together. And we made this question simpler by making the table frictionless and by making the pulley ideal. An ideal pulley is a pulley where you don't worry about the friction. It just spins so smoothly. You also don't worry about the mass of the pulley. You assume that it's got no mass either. Okay, so it's an ideal pulley and it's a frictionless surface. We have to calculate the acceleration of the system when we let it go and the tension in the rope. Okay, so first I'll call the acceleration part A. The acceleration of the system, you want to think about what forces are driving the system to move. And the force that's driving the system to move is the force of gravity on the 4 kilogram block. So the force of gravity on the 4 kg block is what causes the whole system to accelerate. There's no other forces counteracting the 4 kilograms gravity, okay, because there's no friction on the 6 kilogram block. All right, so then what we'll do is I'm going to go with Newton's second law again. And say the acceleration of the whole system, I'll put SYS for system, is going to be the net force on the whole system divided by the mass of the whole system. Okay, the net force on the system is simply going to be the force of gravity on the 4 kilogram block. Whereas the mass of the system is going to be the sum of the two masses together, 4 plus 6. All right, the force of gravity on the 4 kilogram block is going to be 4 times g, 9.8. And the total mass for 4 plus 6 is 10. So that's what I'm going to calculate out for the acceleration of the system. I get 3.92. I'm just going to underline two significant figures. Okay, now in terms of the direction here, there's two directions. The 4 kilogram block goes down, whereas the 6 kilogram block goes to the right. So I'm not really going to write all that detail out. The next part asks us to find the tension of the rope. And I'm going to do that the same way that I did the bucket question. I'm going to focus on one of the objects only. I think I'll choose the 4 kilogram block. So the 4 kilogram block has the force of gravity on it, and it's got tension because it's tied to a rope as well. Okay, we've got to find out that tension. The tension is smaller than gravity because the block is going to be accelerating down. So same as before, Newton's second law, F net equals ma. However, the net force, since gravity is bigger than tension, I'm going to write it as the magnitude of the force of gravity minus the magnitude of the force of tension equals mass times the magnitude of acceleration. Okay, this time when I isolate for tension, I will first subtract Fg from both sides. Okay, so that's subtracting Fg from both sides. Now I've got negative tension isolated. So to get positive tension, I multiply both sides by -1. That effectively just changes the sign of every term. Change the sign of every term. And I'm almost done. I'm going to replace the force of gravity with mg. I'll factor out the m again. And fill in the values. So the mass of the block we're doing here is just 4 kilograms. And then we have 9.8 minus 3.92. I'll get that in the calculator. And to two significant digits, I get 24 newtons. All right, so this video was a lot longer than the others. Actually, that's why I was trying to talk fast as well. That's why some of the explanation might have been a bit fast here. So I'm going to post these problems with the full solutions on Google Classroom so you have access to them. And now it's time for you to try out the problem set to close off the week.